That is, what I've got written here is the one of the three versions of the law of cosines. You're only going to need to know one, and then just kind of jockey your variables around to get the other ones if you want the other ones. They're just the other ones are developed because of the fact of how we set up the first equation, and we actually derive it. It only solves essentially for one side length A. Then how do I go about solving for a side length of B or the side length of C? It's just through the same exact procedure, just looking at maybe different, essentially altitudes of the triangle. So I actually want to go through the proof of this with you. It's not too bad for as complicated as this formula looks. The proof really isn't all that difficult. Okay, I'm going to call this A. Lowercase a there. This would be capital B, and then lowercase b over here. Making that capital C, and then this will be lowercase c. Now, so the idea is this formula right here only solves for A. It only solves for that lowercase a. If I wanted to kind of rework things, I would need to, maybe try. So how would I use the law of cosines to solve for B? And that all comes from just kind of repositioning an altitude. We know that every triangle has three altitudes. An altitude is simply the segment that goes from a vertex perpendicular to the opposite side. So we know that exists in here, right, from C. So that one from C to segment AB is going to eventually get us that formula. Okay. Now I'm going to call that dotted line. I'm going to call it H. Okay. And I'm going to call this point down here capital D. Not a huge necessity to have capital D there, but I'm going to put it in. Now I want to talk about A to D. I want to know what that distance is, so or have a component, a variable for that distance. So I'm going to call that X. Okay, so that's A to D. Now, if, just going to follow the highlight here, if this distance x plus this distance db, they need to add up to c, don't they? So what could I call d to be? C minus x. Do you guys agree that c minus x plus x gives me c? So those are the parts of the triangle that I need to show that the law of cosines is this formula. Okay. Would you guys agree that there are two triangles up here? There's actually three, right? But let's just focus on that triangle right there. Do you know all three sides of that triangle, variable-wise? So let's link them together. Let's say that x squared plus h squared is equal to what? B squared. Fag right there. That's all that is, right? Would you say that we could do the same thing over here in this green triangle? Can I say in the green triangle that h squared plus c minus x squared is equal to a squared? Okay. Now I'm going to do a little bit of work here, because c minus x squared actually means this, right? C minus x times c minus x. Can we FOIL that out? C times c would be c squared. I'm going to get negative cx and then negative cx, so it becomes negative 2cx's. And then plus x squared is equal to a squared, right? I just want to draw some comparisons here to where we think we need to go, or where we know we need to go. We need to get to this, right? And so far, would you agree that we have that correct? Would you agree that there's a c squared on the left-hand side? There's a c squared there, right? There's a minus 2c here. So I've got the minus 2 there, and I've got the c. I see I didn't need to kind of deal with the b and the cosine of a yet. And I don't have the b squared yet, right? But let's look at this. Look at that h squared, and look at that x squared. Can you replace that with b squared? Does that kind of make sense? Okay. Now the reason we can do that, think about this. This thing here in black came from this triangle here, right? But when we FOILed that out, some components that showed up were x squared and h squared, which were components that are actually from the yellow triangle, right? This was a formula from the yellow triangle. So that means that we can take these x's and these h's and interchange them over here. So now I'm going to rewrite this as, instead of this h squared and x squared, I'm going to rewrite that as b squared. And I got plus c squared minus 2cx is equal to, I'm just going to put the a squared out in front here, is equal to a squared. Is that pretty close to this format up here? A squared is equal to b squared plus c squared minus 2. Now I need this b cosine of a to show up, right? All right, well, a is this angle here, correct? What side would x be for that angle a? That'd be adjacent, right? What side is b for that angle a? Hypotenuse. What uses adjacent and hypotenuse? Cosine. So can I write another formula here that says cosine of a is equal to x over b? Will that allow me to eventually get rid of this x down there? Can I solve this red equation for x? B cosine of a is equal to x, right? So now I'm gonna replace that thing there with b cosine of a. So I get a squared is equal to b squared plus c squared minus 2c times b times cosine of a. And now that then ends up being our law of cosines, right? Does that make sense? So you see that this is essentially just the Pythagorean theorem. The proof of this is the Pythagorean theorem accompanied with one trig ratio of cosine and three things of substitution. Okay. So that's nice, and that's finding a, the length a. Now, in the event of us actually doing calculations, we have to take the square root of that later to find a, right? Right, that solves for a squared. Some textbooks will have it solved for a. Some, a lot of times, most of them have it solved for a squared. Okay, so you should do that extra square rooting process after you plug things in. But what this allows us to do, look at the things that this solves for. If I go back to just the general generic ABC arrangement of our triangles, what this is going to do for us is going to find that value there. And the components that you need to be able to find that A are this B, that angle, and this C, right? Those are the only things that are down here, B, C, and that angle. So if we look at this, that's a side, an included angle, and a side. So when we're doing the law of cosines, the orientation of parts that you're using the most often is side angle side, okay? But we can also do the law of cosines with side, side, side. Okay, those are the two arrangements that allow us to use this formula. Now, that just solves for A, right? Well, what if I wanted to solve for angle C? Well, if I wanted to solve, or sorry, not angle C, let's say I want to solve for side C. Okay, then if I'm going to solve for side C, I'm going to need the angle opposite it, and then I'm going to need the two sides that are sandwiching it. Does that make sense? Okay, so that's where you get the additional kind of three total variations of the law of cosines, because we're solving for three different side lengths of the triangle. And really, to get those additional formats is simply to, if I'm trying to solve for C, it's probably looking at maybe that altitude as H, going through the Pythagorean theorem again, and that will allow you to solve for that distance C. If I want to solve for distance B, then maybe I use that altitude. Does that kind of make sense? Okay. What I think is useful, because I'm not going to tell you to memorize all three of these. Okay. Because they're really the same. This is kind of a pattern that we see as we look at the objects that are being solved for in the formula, a squared, b squared, and c squared, and the angles that kind of finish off the formula, the last input value that you use in your formulas, capital A, capital B, capital C, they're kind of mirror images of one another, right? If I start looking for distance A, okay, at the beginning of my equation, then angle A has to be at the other end, okay? So they're kind of like bookends in a bookshelf, right? And they got to match up. So you'll never have A out front and then capital B in the back, okay? And angle A and side A are always opposite each other, right? Everything else is the remaining two sides, okay? Your B squared, your C squared, those are the remaining two sides, right? And then your B times C is your remaining two sides. The addition there is commutative. The multiplication there with B and C is commutative, so you can flip-flop them if you need to. If you look through there, it's static addition, it's static subtraction, okay? And those twos are constant, right? So I don't think it's beneficial to learn all three, but I want you to know why all three of them are usually written or provided. Is that all right? Okay. So they're going to ask us, can we solve a triangle using this formula? So we should. The best thing, guys, you can do this. Some people are really in tune to being able to visualize this without a picture, but I would think the safest thing to do is to always draw a picture with these things. Now, your picture doesn't have to be great, doesn't have to be to scale, doesn't have to be accurate. It's just something that's going to allow you to organize your thoughts. So we'll call that A, B, C. C is going to be 82.4 degrees. Side A is 212, and side B is 388. Now, I just want to kind of, last class we did this at the end of the problem, but it might be good to kind of think about this initially. If you guys remember back to geometry, we had what we call a triangle inequality theorem, okay? Which basically meant that with given three sides of a triangle, not always will your three sides touch. And what I mean by that, if I look at, let's see here, let's go to, figure out where I put it. There we go. I'm not sure if I was using this at the point that I had you guys in geometry or not, but let's see. Okay, so what happens with, if I give you three segments of a triangle, we should know that there are certain arrangements of distances in which I'm allowed to kind of make them rotate around vertices so that the three segments actually create three vertices and I get a triangle, right? But there are relationships that exist, okay, where I will no longer be able to get those things to connect to create a third vertex, right? Okay. And essentially the idea is if I gave you these two side lengths right there, okay, the maximum that the red one could be, you may have a number that they might think that could be a maximum that the red one could be. Okay, 10 will work, but there should be another maximum. 11 will not work. There's a number very, very close to 11 that will work. 10.99999999999 will work. Okay. So really, what we do is we define our kind of boundaries to how big the red one could be. Is at first we add the numbers together, and that would give me 11, right? Okay. And then I subtract the numbers, and that would give me, 9 and minus 2 would give me 7. Does that make sense? Okay. So what happens then is that my third side, my red side, could be between 7 and 11. Okay? Let's write third side here. And as long as this red side is between those numbers, we will end up getting a triangle. Does that make sense? Okay. Now, right now, it's not going to give me a triangle because it's exactly at 11. So you see that they intersect right there, right? And that's not a triangle. It's maybe a collapsed triangle. But once it becomes like 10.999999, we could have a situation kind of like that, where it's a really, really, really short triangle, right? Does that make sense? Okay. But if I can find this red value to be anywhere between 7 and 11, now we will get the ability to get those to intersect to create a triangle, right? Okay. Outside of 7, let's say I take this thing down to 6, and now that blue side and that green side, those endpoints will never be able to touch. Does that make sense? So I don't get a triangle there. So the reason I bring that up is I think it's important for us to look at the values here of 388 and 212 and to know that when I'm done, my value of my third side should be in the range. Let's clear all this junk out. Should be in the range of 388 plus 212, so 600, and 388 minus 212, 176. So my answer should be between 176 and 600. Now, is that something that you're going to do every single time? Probably not. Okay. But it is something to think about as we get answers, start getting values, and we use our calculator. Because what if I get a number outside it? Maybe something I look at is, okay, what was my mode on my calculator? Because I think I'm doing things right, but what's my mode? Okay. Or if I get a number that's outside that range, I think, okay, maybe I just solved for c squared instead of c. All right. So, and that's something I always get people to do. All tests, they go through all the formatting correctly, they know the formula correctly, but then they grab their calculator, do something wrong with their calculator, or they don't go far enough with the formula to actually find the actual length. They a lot of times write the length squared as the answer. But having that kind of the back of my head might remind me what I need to continue to do, okay, before I finalize my problem. So we're going to try to solve here for, really the only thing we can solve here is C, okay, using the law of cosines. Could I use maybe the law of sines to find A or B in this case? Can I? Let's say I want to find A using the law of sines. I go sine of A over 212, right? And then I use sine of, got to use 82.4, right? But what's that going to be over? C. How many variables you got there? 2. So I can't use the law of sines yet to find A or B. But once I find C, then I can get into the law of sines to find other stuff. Is that all right? Okay. So I'm going to say that that C squared is what I'm looking for. Okay. In my formula, then, the angle opposite C, which is 82.4, is going to be at the end of my formula. Okay, those are the bookends of my formula, right? The side and the angle opposite that side. Now, everything else in the middle is always going to be something squared plus something squared minus 2 times the product of those somethings. Okay? What can I put here? 212, does that work? Can I put 388 there? Yeah. Or I put, because the commutative property 388 could go there. They could be flip-flop. So now, once I figure those out, there's 212 and 388 right there. And now you have everything plugged in. So you can grab your calculator. Just type it in directly the way you see it written, and you should be okay. So 212 squared plus 388 squared minus 2 times 212. 388. Cosine then of 82.4. Should give you that number there. And this is what I'm saying. I know that my answer should be between 176 and 600, right? Hopefully that gives you an understanding then that your number right now is way outside that. You've got to continue to work, right? So what do I do with that number then? Square root. Okay, now, just kind of shortcuts, kind of being efficient with my calculator. What power can I raise it to so it's the same thing as square rooting? Raising to what power is the same thing as square root? 1/2. So I'm actually going to just hit the caret key, take the previous answer, raise it to the 0.5. I think it cuts out maybe having to use 2 other additional keys. So 416. Does that number fall in that range of 176 to 600? Yeah, so that will make a triangle. Those are 3 distances that will connect end to end. All right, so now we've got C as that 416 number. And I'm going to write it this way, just approximately 416. Maybe I should go 81. But now I'm going to try to find A and B, right? And just for the sake of using the formula for law of cosines to find an angle, I'm going to use the law of cosines here. You have options, okay? And your options are, once you start finding missing parts, you set off initially how to use law of cosines. You found one missing part. That actually opens up the door for you to now use the law of sines. Does that make sense? Find the missing parts. Just be careful that if you do that, and the parts that you use are angle side side, you have developed the ambiguous case, and you got to pay attention to your work and what it's telling you about the ambiguous case. Okay, we kind of ran into that issue in the next question in the last class, and see if we can kind of analyze that after we do this with you guys as well. But the thing is, I can see I find A or B. And once I find A or B, I can subtract that sum from 180, right? And get the remaining angle. So let's just try to find maybe angle A here. Okay? So I'm going to try to find angle A. That angle is what I'm interested in. I know the side opposite, right? So there's a law of cosine formula that says A squared should equal B squared plus C squared minus 2BC's cosine of capital A. And we are now currently looking for capital A, right? So we should know everything else in that formula. We know A is 212, so I have 212 squared. We know B is 388. So again, B or C are the two sides that are sandwiching the angle that I'm interested in. It's either the angle that I'm using or the angle that I'm trying to find. So you have 388. I'll have 212 here. Oh, not 212. It's now 416.81, right? That's the value that I found. I'll square that. Minus then 2. 388. Got that 416 number. I'm just going to write 416 right now. We'll talk about that in a minute. And then cosine of A. Can we do that? Now that's kind of ugly, and it doesn't have A solved for, right? We've got to isolate A. So let's try to get this thing by itself first. So in doing that, I've got to move over the components that are being added together, right? So I'm going to get 212 squared minus 388 squared minus 416.81 squared. That will then give me ultimately something that looks like that, right? Does that make sense? Now, what would this number out in front here, this product, what would you call that for cosine of A? What would you call that number? It is starts with C, ends with coefficient. Okay. So if I've got coefficient out here, now it's written as a product, right? An implied product. So how do I get rid of those coefficients? Divide. So it should look like that then, right? Now how do I get this A all by itself? Cosine inverse. Okay, so cosine inverse both sides. It will leave me that A. And let's see here. On this side, it should look like that. Now, if you're a person that writes that all out by hand, which is great, hopefully you do that, you can still mess this up with your calculator. So if I just put the parentheses for the cosine inverse up there, my calculator is going to do order of operations, multiply, divide, before it does add and subtract. Does that make sense? Okay. So we'll go through, it'll do all the exponent stuff that we want it to. But then it's going to take that 41681 number that has been squared, and it's going to divide it by -2 first. Does that make sense? And now it's going to rewrite that as a product, so now a quotient that we really don't have written up there. Does that make sense? So in order to, this is just what you got to pay attention to all the time. In order to make sure that you do the right thing with your calculator, if your numerators or denominators have multiple operations in it, or just one operation in it, the safest thing to do, the most conservative thing to do, is to put an extra set of parentheses to encapsulate your numerator and tell my calculator, we want the calculator to calculate that thing first. Store that number. Then go through and calculate that thing second. Store that number. Then divide those two stored numbers. Does that make sense? If I don't put those red parentheses in there, it won't do that. Okay. So now I'm going to grab my calculator and try to type that in. All right, here's the thing before we do this. Okay, I've got that 416 number right there. It's really accessible to me. I know that last 9, the 929 there, that last 9 might be a 9 or might be an 8. There might be there's rounding error incorporated there, right? The way my calculator is presented to me. But I want to minimize rounding error as much as possible, find angle A here. So when I go to my formula, 416.81 or 416.809, or do I use 8.096? There's debate there, right? And it's all dependent on how much they want me to round my answer. My thought is, let's try to eliminate all rounding error as much as we can. Can I tell my calculator to store that number as X? Just hit the STO button. Brings up this arrow, which means store. As that variable, hit enter. So now every time my calculator sees me type in an X, it's actually typing in a 416.8095929. And it's actually storing the numbers that are to the right of this as well. Does that make sense? So I'm not going to have any rounding error if I do this way. So I'm going to go second cosine. Parenthesis, that's the red parenthesis. I'll go 212 squared minus 388 squared minus then 416.81, which we have stored as X, right? Weird. I'll square that. Now this parenthesis will be that red parenthesis there. Now we'll divide. That parenthesis is this first red parenthesis in the denominator. Now I'll type in -2 times 388 times 212, or sorry, 416.81, but that was what our X was, right? Close the parenthesis off. Okay, now I need to close the parenthesis off for the cosine inverse. Hit enter, and I get 30.27 as my angle. Okay. Now what's nice about that is that last value of 4 there, the 324 at the end, It's either a 4, okay, or it's a 3. Does that make sense? That's the only place now that I have issues with rounding here, which is nice to use my calculator to do this because a lot of times in WebAssign or the ACT or something like that, they're going to ask you, round this to 3 decimal places, round it to 4 decimal places, something like that. Where if I'm going to use rounded values inside my calculations, then my rounded values need to be more than 3 or 4 decimal places, right? So why not allow my calculator just to store those values as exact values? Okay. And you can store your calculator up to, feasibly 26 separate things. Okay? I used X. I could use A, B, C, and start putting all those things together inside a written out expression. Now, if I've got that, okay, I know one angle was defined initially as 82.4, right? Can I add this number to 82.4? Remove that from 180. And now my remaining third angle is 67.32 degrees. Does that make sense, everybody? Okay. The law of sines would have also gotten into those things. Okay, there's nothing wrong with using the law of sines. My only concern with the law of sines is in the event that the ambiguous case may show. Okay, there is debate, and I'm going to leave it up to you what you want to do. If you're a person that says I'm not going to do that algebra every single time that they're asking me for an angle measurement, because there's a lot of stuff there, right? The subtraction, the division, all that kind of stuff. You might be a person that says, I'm going to do this. I'm going to say that a squared minus b squared minus c squared is equal to negative 2bc cosine a. You do the algebra here, right? Does that make sense? Divide both sides by negative 2bc, so we get a squared minus b squared minus c squared divided by negative 2bc is equal to cosine of a now. You inverse both sides. So there is the law of cosines if you're looking for an angle. Is that okay? Now the only thing that you got to know here is that if I take 10 minus 3 minus 2, is that different than 3 minus 10 minus 2? Is subtraction commutative? No, I cannot flip-flop things. 2 minus 3 is negative 1, right? But 3 minus 2 is positive 1. All right? So when I look at the a squared minus b squared minus c squared, that stuff, that order is important. Okay? And now how do you get the order correct? And it simply says, if we look at the relationships, the angle that you're looking for and that first side length have to match. Okay, does that make sense? And everything after that doesn't really matter, because if I have 10 minus 2 minus 1, which would be 7, right? It's the same thing as 10 minus 1 minus 2, still 7. So I could flip-flop the b squared minus c squared if I wanted to. Okay? That a squared has to be the side that's opposite my angle I'm looking for. That has to be first. Okay? You can memorize that formula, or you can just do the algebra like we did over here every time you need to find an angle. My argument, my thought is, think about a lot of the formulas that you guys get in this course and other courses, maybe science classes. Those formulas are designed and solve for those components. For instance, this is solved for A because most of the time I'm trying to solve for a distance in the law of cosines. Does that make sense? There's another formula down here we'll talk about maybe tomorrow, if we talk about it at all. It's called Heron's formula. It's an area formula. It's solved for A because I'm most of the time interested in solving for an area, right? I'm not interested in solving for S, which we call a semi-perimeter, okay? But we could go through the formula and do that, okay? Just real quick, guys, I want to go through another example here, just briefly, on how we can maybe use the law of cosines. This is a side orientation, right? Let's try to find angle A. Okay, so if I have Um, angle A is what I'm looking for. So A squared, or this side length here, should be what starts off the equation, right? And then cosine of that angle over there. Now, everything else, okay, will be the sides that sandwich the angle that I'm interested in. Okay, so I take 8 and I square that. I take C and I square that. And it's minus 2 times the product of B and C, which is 96. Okay, sometimes when you're dealing with nice numbers, like 8, 12, and 5, maybe you just write things out like this. Okay, in contrast to the last question, I'm not squaring 388 in my head or 212 in my head, right? You can do this, you get 25. This number here is 208. I need to remove that from both sides, right? That will then equal negative 96 times 2 is 192. Cosine of angle A. So now can I take 25 minus 208 divided by negative 192? That should give me cosine of A. So if I inverse both sides, it gives me A, right? The only thing here, you want 25 minus 208 divided by negative 192, right? If I don't put parentheses around that, my calculator won't do the order operations the way I want it to. So second cosine, parentheses 25 minus 208. Obviously, you guys don't want to write it as 25. You want to left it as 5 squared. You want to leave the 64 as 8 squared and all that kind of stuff. By all means, do that. There's nothing wrong with that. You can use your calculator anyways. So if you want to keep things unsimplified, I don't have an issue with that. So we'll go to yeah. So right next to parentheses. So 17.61 is that angle A. All right, so here's what we ran into last class, and we'll briefly discuss it here. Once I find angle A, I want to find angle C and angle B. And you can go find angle C and angle B using the law of cosines if you want. But if you want to use the law of sines, there's absolutely nothing wrong with it. Sine of 17.61 over 5 should equal the sine of C over 12, right? Does that make sense? Now, the parts that I used there were an angle, a side of 5, and a side of 12, right? I use an angle side, right? That's the ambiguous case. Now, maybe you don't recognize that right away, and to be honest with you, in the last class we didn't, but when I go through and I try to solve for this angle, I'm going to get essentially C is equal to, I'll leave for you guys to do all the algebra here, but it becomes sine inverse of 12 sine of 17.61 over 5. If I type that in, sine inverse 12 times sine 17.61 divided by 5. Because I'm using my calculator, maybe I should have probably chosen a better number than 17.61. I could have recalled this number up here. But regardless, I get that number there. 46, right? So if that's 46, that makes angle B over 100 degrees. Does that make sense? Can that be true? Why? Well, yeah, but those three numbers are still out. So what I'm doing, I would take that number plus that number, remove that from 180, and it'll give me that number. So that remaining angle B is 115. Is that possible? Look at your side lengths and your angle measurements. Can angle C be smaller than angle B? Why not? Yes, the triangle inequality said the largest angle has to be across from the longest side, right? So we got that 46. We actually need to use the supplement of that 46 to be angle C. We'll talk about that more in the next couple days. Okay, I apologize for the break, but I just got to Wildcat time, or through Wildcat time in my plan period to finish this question up. Okay, sorry about that. But I want to get back to um, discussing when we use the law of sines here to finish this problem off. We come across um, some geometry that doesn't make a whole lot of sense initially. What happened was we took this law of sines proportion here, and we ended up getting, it's here in blue, I know you can't see it, so let me write it over here, sine inverse of 12 sine 17.61 over 5, and that should give me angle C. Well, when I calculate that, it gives me angle C to be this number right here, this 46 point, I'm just going to say 46.5 number. Angle C, 46.5. Okay, making then if we go through the idea of having 180 degrees in a triangle, it makes this angle here 115 degrees. Well, that doesn't make a whole lot of sense, and if you're not thinking about what's going on here, you're going to run into trouble with final answers. So, because this is indeed wrong. What we should know is that if this is the largest side of the triangle, then opposite it should be the largest angle. And right now that's not obviously happening. Okay, we're seeing that 115 is the largest angle. Okay, so we have some problems. So what's that tell us? It actually tells us that because we used angle side information to go through with this proportion, we actually calculated one of the situations where you could have had the ambiguous case. So really what happens here is that this is not, to match up these three side lengths, this is not 46.5. It is actually going to be the supplement of that. So 180 would give me that number. So 133. So this angle here is got to be 133.4 degrees. And then this one here would be would now be a total of 28.9 degrees. And hopefully that all that makes sense, because you know that's the smallest angle, across from it's the small side. That's the largest angle, across from it is now the longest side, and this is the middle angle, and across from it is the middle side. And because these two numbers they're relatively close together, so 8 and 5 should be relatively close together. So that's kind of the idea going on there with that question. You do kind of miss out on all of that if you're a person that says, I'm not going to deal with the law of sines, I don't like the law of sines in this situation, or maybe I know it's going to maybe potentially bring in the ambiguous case, and I got to use other facts and other thoughts to verify solutions. You might say, well, I'm just going to strictly say, I'm going to stick with the law of cosines. I'm going to say 12 squared is equal to 8 squared plus 5 squared minus 2 times 8 times 5 cosine of C. Eventually that's going to give you 12 squared minus 8 squared minus 5 squared divided by negative 2 times 8 times 5. And we'll cosine inverse that to get yourself C. If you type that in, let's see what that gives us. So cosine inverse 12 squared minus 64 minus 25 divided then by negative 2 times 8 times 5. Calculate that, and there you see the 133, which would have been that number right there, which we found by taking 180 minus the 46 number. I think it's 46, yeah, 46.55 that the law of sines gave us. Okay, so 133 is that angle. You got two approaches to find it. My thought is, my suggestion is pay attention to other properties because they need to be maintained. The inequalities of triangles need to be maintained. So if you do ever end up using law signs, just kind of keep in the back of your mind, you got to make sure that all other characteristics and features are not getting violated. Remember, in mathematics, one statement cannot contradict another. So the law signs cannot contradict the fact that that angle there has to be bigger because that side there is bigger than the other two. And to avoid that, maybe you always use law of cosines. Okay, the payoff to avoiding this is a simpler formula, but the payoff of using a more complicated formula is the not having the need to check ambiguous cases and stuff like that. Hopefully that helps. As you go through the 5-6 assignment, I'm anticipating some questions over that. There are some story problems on there that are challenging. They're going to make you think. They're going to have to draw pictures and redraw pictures. But hopefully those story problems give you kind of insight of why we use law of cosines, what applications there are for it, and where it becomes useful for us.